So this video is going to be on the MIT 2024 Integration Bee Quarterfinal problems. And we'll look at quarterfinals number 1 that had the following problems. Problem 1, problem 2, problem 3, and then tiebreaker problem number 1, and then tiebreaker problem number 2. So very interesting problems. And then quarterfinals number 2 that had problem number 1, problem number 2, problem number 3, and then quarterfinals number 3 that had problem 1, problem 2, problem 3. And lastly, quarterfinals number 4 that had obviously problem number 1, problem number 2, and problem 3. So I hope you stay tuned and locked as we go and try and solve each individual problem. MIT 2024 Integration Bee Quarterfinals is our main focus here. Problem number 1 of quarterfinals number 1 is the indefinite integral of the natural logarithm or natural log of x, open bracket, x over e all to the power x plus open bracket e over x to the power x close bracket. Very interesting problem.
The way I would go about solving this problem is I would organize or reorganize this problem a little bit. And how I would do that is by expressing the second part here, e over x to the power x, such that it is similar to the x over e to the power x. So as you can see, we have these similar terms, albeit that on the second part here, this is in the denominator, or it's a reciprocal of the first one. So what we'll do here is we would want to substitute for that. That is the instinct that comes to mind, to try and substitute for the complex parts with this more simpler tractable expressions. So we say let y be equal to x over e to the power x, such that natural logarithm of y is the same as natural logarithm of x over e to the power x. Using the rules of logarithm, we can take this power into the constant part there. So we have natural logarithm of y being equal to x times natural logarithm of x. And since we have a division here, we can subtract this in the separate log function formats, so that we have x times natural logarithm of x minus x natural logarithm of e. And natural logarithm of e is the same as 1, so we have natural logarithm of y be equal to x log x minus x. So the derivative of natural logarithm of y is 1 over y dy dx is equals to, since we have a product of x and natural logarithm of x, we first of all differentiate x, and then we differentiate natural logarithm of x. So we have here, when we differentiate x, we are left with natural logarithm of x plus x, and when we differentiate natural logarithm of x, we have 1 over x, and then minus, when we differentiate x, we have 1. So this here and that cancels, so we're left with 1, and so we're left with 1 over y dy dx being equal to natural logarithm of x plus 1 minus 1, and this 2 would cancel out, so we have a 0 ensuing. So we have 1 over y dy dx being equal to natural logarithm of x, so that dy over y can be used to replace natural logarithm of x dx in the event that we are substituting y for x over e to the power x. So going forward, since we have this as our expression, our initial integration, we could now take this natural logarithm of x and put it next to the dx. So here we would substitute this with dy over y, and this would be y and this would be y. So we have substituting for x over e to the power x with y, we have y plus 1 over y, all into brackets, and then we have 1 over y dy. So this further becomes, when you multiply 1 over y across, we have 1 plus y, 1 plus 1 over y squared. And when we integrate that, we have, in place of 1, we have y. In place of 1 over y squared, we have negative 1 over y. And then we have integration constant there. But since we substituted, we say that y is equals to x over e to the power x, our solution therefore for the original problem, the integral of natural logarithm of x times in bracket x over e to the power x plus 1 over 1 over x to the power 1 over x over e to the power x. For the y, we have now x over e to the power x minus 1 over y is 1 over x over e to the power x plus 1. And now we could just play around with the expression here by bringing e on top. We have x over e to the power x minus e over x to the power x plus c as our answer. So this is our answer. I think that's what was provided in the solution for this integration B. Thank you so much. I hope you did enjoy following along. If you have any question or alternative solution to this problem, please feel free to share in the comment section. But other than that, we do encourage you to consider subscribing to our channel. And yeah, if you like it, please leave a like on our video. Thank you. Until next time.
So on to the quarterfinals number 1, problem 2, which is the definite integral from x equals to 0 to x tending to infinity of sine cube of x over x. It's another very interesting problem. I hope you enjoy it.
Going on to the solution to this problem, first of all, this is an interesting problem. How I would like to solve it is by removing the third power there and substituting it with a double or triple angle formulation. So sine cube x is the same as sine squared x times sine x, and if we have cosine 2x, cosine 2x is the same as 1 minus 2 sine squared x, and when we make sine squared x the subject, we get 1 minus cosine 2x over 2. So if we substitute for this sine squared x with 1 minus cosine 2x over 2, we get sine x over x times 1 minus cosine 2x over 2. Multiplied it across, we get half because we pull this one here, these two here out, times sine x over a half times the integral of sine x over x from x equals 0 to x tending to infinity minus a half times the integral from x equals 0 to infinity of 1 over x times sine x times cosine 2x. Now we also would like to express this formalism into a more easier expression. So for example, if you had sine 3x, that's the same as sine x plus sine 2x, sine x plus 2x, which is the same as sine x cosine x plus sine 2x cosine x, and then negative sine x is the same as sine x minus sine 2x, which is the same as sine x cosine x minus sine 2x cosine x. Now, if we draw a line and we added the left hand side and the right hand sides respectively, on the left hand side we have sine 3x minus sine x, which is equals to, since this and that cancel out, we're left with 2 sine x cosine x. And therefore, sine x cosine 2x is the same as sine 3x minus sine x over 2. So we can use this to substitute for this expression here. And so we have our integral now reducing to a half, integral of sine x over x minus half times the integral of 1 over x sine 3x minus sine x over 2. So we can separate this into two separate integrals, and that's what we're going to show here. Eventually we have in the second part a quarter, the integral of sine 3x over x from x equals 0 to x tending to infinity. So what we do have is now 3/4, because we've added this with this, minus a quarter, the integral of sine 3x over x from x equals 0 to x tending to infinity. Now, how we handle this 3x, we can say let u be equal to 3x, such as du is equal to 3 dx, and so we can now substitute 3x with u, and therefore dx we can substitute with the du over 3, and x is the same as u over 3. And as you can see, this and that cancel out, and we're left with a quarter for the second part times the integral of sine u over u du from u equals to 0 to x u tends to infinity. So we can still replace this u with x and then subtract that quarter from this other side, right? As we said, 3/4 integral sine x over x minus a quarter the integral of sine x over x results into a half the integral of sine x over x. And this is where now things start becoming very interesting, because now we can use the famous technique called differentiation under the integral sign or integration sign, or the Feynman integration technique. That's what most people know it as. So we can say let IA be equal to our integration sine x over x times this exponential e to the power negative ax, right? Such that when we get the derivative of that, we are allowed to perform the differentiation under the integration sign. And so what that leads to is dIA dA is the same as negative x, pulling this out, sine x over x times e to the power negative ax. And as you can see, this and that cancel. So we are left with a very tractable integration, which is negative e to the power negative ax sine x, still from x equals to 0 to x tending to infinity. Now we can now use integration by parts, since negative sine x is the same as the derivative of cosine x. And so using the integration, if for example we have the integration of u dv, dv, this is equals to uv minus the integral of v du. Okay, and since from this expression our v is cosine x and our u is e to the power negative x, as you can see here, we have the uv as e to the power negative x times cosine x minus, and then v du, our v is cosine x, du is the derivative of e to the power negative ax. Going on, we can see that this part here, after we've differentiated this e to the power negative x, we get a negative a that comes out, and that makes this positive. And then this part here is the same as limit of x tending to infinity of e to the power negative ax cosine x minus limit x tending to 0 of e to the power negative x cosine x. As you can see, as x tends to infinity here, this part here tends to 0 because cosine x fluctuates, either -1, +1, it keeps oscillating. But um, as x tends to infinity, this part here becomes 0, so this part becomes 0. The same thing here. When x tends to 0, this part here tends to 1, and cosine tends to 1. So we have -1 in the first place there, and then we have a times the integral of e ax cosine x. Right? Now we'll continue again with the integration by parts. So cosine x is the same as the derivative of sine x, and so we'll use the same approach where we say uv vb sine x is e to the power negative x sine x, and then minus a here, the integral of v du. So v sine x du is the derivative of e to the power negative x. So we have on the left hand side, we have negative of 1. This -1 comes here, and then this, as this goes this side, becomes negative a squared. So when we pull the negative outside, we have -1 plus a squared, the integral of e to the power ax sine x, and this is the same as the derivative of ia with respect to a is equals to -1. And so this dIa dA, which is negative, the integral of e to the power negative x sine x is the same as, when we divide this constant on both sides, the same as -1 divided by 1 plus a squared. Now, interestingly, we can now bring back dIa dA, and then in order to get ia, we have to integrate -1 over 1 plus a squared. This is a very famous integral. 1 over 1 plus x squared is the same as the arctangent when integrated. So we get the negative arctangent of a plus the integration constant. Now our original integral is actually sine x over x, which is the same as I0 when this a here is 0, right? So that means that the integral of sine x over x from x equals 0 to x tending to infinity is going to be the arctangent limit of a tending to um, to 0 uh, of this negative arctangent plus integration constant. But in order to find this integration constant, when a tends to infinity, this entire integral collapses to 0. So that's why when a tends to infinity, we have 0 is equals to negative the limit of a tending to infinity of the arctangent of a plus c, the integration constant. Since when a tends to infinity of the arctangent of a means that that is pi over 2, and on the left hand side we have 0. So essentially c, the integration constant, is pi over 2. And so that when we try now to solve the integration of sine x over x, which is the same as I0, which is equals to the negative arctangent of 0 plus c. Arctangent of 0 is 0, but c is pi over 2. So I0, which is the integral of sine x over x from x to 0 to x tending to infinity, is the same as pi over 2. But we were able to show that our integral of sine cube x over x is the same as half the integration from x equals 0 to infinity of sine x over x. And so our half times pi over 2 is our answer, which is pi over 4. And this is the answer to our problem. So thank you so much for following us along. I'm kind of a little bit under the weather, but I hope you're able to follow. If you do have any questions, please don't hesitate to leave a comment in the comment section. We love to hear from you. For those of you who haven't subscribed, please do consider subscribing to our channel. We would love your support because that would give us that extra visibility that we need. Thank you very much. Until next time, à tout à l'heure, à la prochaine fois.
So on to problem number 3 of the quarterfinals number 1, which is indefinite integral of the determinant of the matrix x 1 0 0 0 1 x 1 0 0 0 1 x 1 0 0 0 1 x 1 0 0 0 1 x. Another very interesting problem. I hope you enjoy it.
Going on to the solution to this problem now, obviously the heavy lifting really lies in determining or finding the determinant of this matrix. And what I usually do is so I do assign the signs here. So at the top, if I pick, for example, x as our constant, I have a plus as the sign, and then for 1, because essentially what finding the determinant is taking this out as a constant and finding the determinant of this, and then taking this as a sign for the constant, and then using this as a constant, taking this as our next constant. This is the sign of the constant, and then you find the determinant of these lower rows, excluding this row, right? So how to represent that is we have x, and then we have this here, which is what we're showing here. And then we have minus, picking this minus, and then we have a hidden 1 here. And then now we have taken the determinant of the lower rows, excluding this middle column here. So it's, you see, 1, 1, then this 1, 1, 0, 0, 0, x, 0, x, 1, 0, 0, 1, 0, 1, x, 1, 0, 0, jump to 0, 0, 0, 1, x. And the same process continues. There's a nested. So again, you pick x as your constant, and then the sign. So you continue with that nested approach for the succeeding determinants, right? Um, so what we've done here is we pulled out the x and then now taking this x here plus x and then the determinant of this minus 1 and the determinant of this lower rows excluding this, and this is what we see here. And here we have 1, 1. So first of all, keeping this negative here, and then we have a hidden 1 here coming from here, and then we're taking this here, determinant of that, x1, 0, 1, x1, 0, and then this negative 1, taking the sign 1 here, and then taking the determinant of this lower rows, excluding this column here. And so this is 0, 1, 0, 0, x1, 0, 1, x, jumping this obviously. And the process continues, again, we have this constant here, and then now we're back here, and then this negative 1 here, and then we're taking this 1, 1, 0, x. Same thing here, since this is 1, 1, so we have a hidden 1 here, hidden 1 here, and then we have first of all determinant of this, and then the determinant of 0, 1, 0, x. Same thing happens for the succeeding. And then so we have now the determinant of this 2 by 2 matrix is x squared minus 1. And then this is 1 times x minus 0 times 1. So x minus 0. This is x times x squared minus 1. And 0 times x minus 0 times 1. So 0 minus 0. Here x times x minus 1. 1 times x minus 0 here, and then here 0. So this whole entire thing is going to 0 because we have a 0 as a constant here. But looking at the determinant of this is x times x, which is x squared minus 1, x times 0 here, minus times 0, so 0 times 0. Okay, so going further, we now multiply this x across, so we have x cubed minus x, and then minus this x here, and then here we have x squared minus 1, this is 0, so we've kept it that way, and then multiply this x across, we have x cubed minus x here, and this entire thing is 0, and then we continue further and multiply the x across, so we have first of all, beg your pardon, minus x, this is 2x here, and then now we're going to multiply this x across, so we have x to the power of 4 minus 2x squared minus x squared here minus 1, and then here we have x cubed minus 2x minus x minus x. Then the final x goes in, so we have x to the power 5, and this 2x squared minus x squared is 3x squared times this x, this becomes minus 3x cubed, and then we have plus minus minus plus 1 here times x, we have plus x, and then here we have minus x cubed, and then plus 2x. So this and this becomes 3x, and this minus this becomes 4. So we have now the integral of x to the power of 5 minus 4x cubed plus 3x. And this is very easy to solve because when we integrate that, x to the power of 5 integrated is x to the power 6 over 6 minus x 4x cubed integrated is minus 4x to the power 4 over 4, which is same as minus x to the power 4, and then plus 3x integrated is 3 over 2x squared, plus the integration constant. And this is the answer for this, obviously, initially visibly challenging problem, but when you do your due diligence, it's supposed to boil down to a very simple expression. So thank you again for your attention. I'm still a little bit under the weather, but math is part of the cure for whatever ailment I'm going through. Thank you. Until next time, tout à l'heure, à la prochaine fois.
Still on the MIT 2024 Integration Bee Quarterfinals 1 Tiebreaker problem 1, which is the definite integral from x equals 0 to x equals 2024 of x to the power 2024 times log to the base 2024 of x. Very interesting problem. Hope you enjoy it.
So solving this problem, it's interesting. The first thing is I would like to express the log part here into the base of e. And so how I would do that is we'd have log to the base e of x and log to the base e of 2024 in place of the log to the base 2024. So this is just an easy log rule. And so the denominator here becomes a constant and we can pull it out. And now we are left with x to the power 2024 times log to the base e of x. Now, as it's been a custom here, we usually abbreviate log to the base e as just log, and that is now we have 1 over log 2024 times the integral from x equals to 0 to 2024 of x to the power 2024 and log of x. So we can now go and exploit integration by parts, and x to the power 2024 can be expressed as the derivative of 1 over 2025 times x to the power 2025. And now using integration by parts, where if we have an integral of u dv, the integral would be uv minus the integral of v du. Now, if this is our dv, then our v is 1 over 2025 times x to the power 2025. And therefore, uv would be the product 1 over 2025 times log 2024. First, before I jump there, what I did here was just to pull the constant out. And so that our uv now will be this constant here, 1 over 2025 times log 2024, x to the power 2025 log x, and we apply the limits appropriately, minus the same constant integral of the derivative, our u, du is now 1 over x, and we are still left with our v as x to the power 2025 times the constant. So applying in the limits appropriately, what happens is now x to the power 2025 becomes 2024 to the power 2025 log 2024. And as you can see, what happens here is this and this would cancel. And here, this is a very trivial integral. So in the first part here, we're left 2024, the power 2025 over 2025 minus this same constant. Integrating 2024 is the same as 1 over 2025 times x to the power 2025. Applying the limits appropriately, we are left with, in the second part here, 1 over 2025 squared, this times log 2024. And then the x here becomes now, with this substituting this limit here, 2024 the power 2025. So this happens to actually be the answer that was provided. But yeah, we can maybe try to play around and simplify it a little bit. We have 2024, the power 2025 over 2025. And then this is 2024 over 2025 over 2025 squared times log of 2024. We pull out the base 1 over 2025, but I think as it is simplified enough. So this is our answer. Very easy problem. But yeah, if you have any questions, if you have any alternative way of solving it, we do welcome your comments and feedback. We're here to learn, we're here to grow, and we are here to share. So until next time, it was an absolute pleasure sharing with you our version of the solution. If you haven't subscribed, please do consider subscribing to our channel. Bye-bye.
So on to the MIT 2024 Integration Bee Quarterfinals 1 Tiebreaker problem number 2, which is the limit as t tends to infinity of the integral from x equals to 0 to x equals to 2, open bracket, x to the power negative 2024t times the product from n equals to 1 to x n equals to 2024 of sine, open bracket, n x to the power t. Very, very interesting problem. Hope you get to enjoy it.
So how do we solve this problem? The first step is in just expressing it in a way that is easy to comprehend. So what I did was just to remove this bigger product sign here and express the individual elements just in a way that can allow us to picture things. So we have, first of all, this x to the power negative 2024t can be spread across all the product items or elements in this product term. So we have sine of x to the power t over x to the power t, sine of 2x to the power t over x to the power t, continuing all the way to sine of 2024 xt over x to the power t over x to the power t. So we have these 2024 different elements multiplied together. And the first thing that at least I could visualize here is I see for the limit t tending to infinity of this x to the power t, you see that it tends, x to the power t tends to 0 between 0 and 1. But between 1 and 2, this tends to infinity. So I'd like to divide this integration into two different integrals between 0 and 1 and between 1 and 2. Okay, so that's what we've done, right? Now going forward, since that's what we've gotten, the, the important thing to note here is that since these independent functions here are continuous in both the intervals, we can now go ahead and take the limits as t tends to infinity of the independent product elements, and without losing the generality, or without losing the intention or the answer of what we are trying to aim at. So we've taken this limit and we apply to the individual elements as shown here. Okay, then going forward, as we stated previously, between between 0 and 1, the limit x to the power t is 0, so as t tends to infinity. And then between 1 and 2, when t tends to infinity, x to the power t goes to infinity as well. So the important thing here, since this x to the power t tends to 0 and sine x to the power t, that sine 0 tends to 0 at that point, the denominator also tends to 0, we are going to have to employ a L'Hopital rule for the top integral. And since sine x to the power t, even if x to the power t tends to infinity, it still oscillates between -1 and 1, yet the denominator here tends to infinity. We'll see that these individual terms tend to 0, right? Because the numerators at any point will just oscillate between -1 and 1, +1. So this lower term here would be 0 times 0 times 0 times 0. So effectively, our integral here reduces to only us focusing on the first integral. And we're going to make that a little bit more clear as we go along. So since this is our integral, and as we said, using L'Hopital's rule for the interval x, when x is between 0 and 1, and also noting that between that sign n, that the x to the power t, that is n could be 1, it could be 2, it could be 2024, noting that this function here oscillates between -1 and 1, yet x to the power t tends to infinity in that interval, the lower interval 1 to 2, then we're just going to simplify things. Our integral here degenerates into this. So we've used the L'Hopital rule, and we got in the first derivative with respect to x to the power t of the numerator and denominator. And now we see that the denominator disappears because it's just 1. And so we are left with cosine x to the power t limit with x to the power t tending to 0, 2 cosine 2x to the power t with x to the power t tending to 0. And what this other term here becomes 0, 0, 0, 0. So here, as x to the power t tends to 0, cosine of 0 is definitely 1. And this, since this is 1, as this tends to 0, and we're left with this constant 2, and that continues up to 2024. So we have a product of 1 times 2 times 3 all the way to 2024. Yet this entire term goes to 0, right? Now we're left with the integral of 2024 factorial from x equals to 0 to 1. And we integrate that, we get x with the appropriate limits, 0 and 1. And that means that our answer now, our final answer is 2024 factorial, which is the constant here. And that is our answer. So guys, thank you so much for hanging around with us. I'm beginning to feel better. So yeah, it was an absolute pleasure hanging out with you, solving this problem. If you do have any questions or an alternative way of looking at this problem, we do welcome your input and your suggestions. Here, we do welcome any form of input. We're here to learn, we're here to grow, and we're here to share. Thank you. Until next time, adios.
To quarterfinals number 2, problem number 1, which is the limit as n tends to infinity, open bracket, of the integral from x equals to 0 to x equals to 1 of the summation from k equals to 1 to n of k x to the power 4 over n to the power 5. Another very interesting problem.
Your support will go a long way in giving us that extra visibility that we do need. Now, jumping onto the solution. So one thing I could do to try and simplify this problem is I will want to decouple the k and x, and how I do that is the same as kx to the power 4 is the same as k to the power 4, x to the power 4. And since the summation only entails the k value here, we could now bring the k out and also the n, and then focus on integrating the x term. Then the next stage, I could bring out the n, since um, the n is a constant in here, so I'll bring it out. So we have 1 over n to the power 5, the summation from k equals to 1 to n of k to the power 4, integral of x from x equals to 0 to x equals to 1 of x to the power 4. Now the integral there is simple. What we do get there is a fifth x to the power 5, and we have limits 0 and 1. So when you substitute that limit of these limits, we are left with a fifth on the upper limit and 0 on the lower limit. So we have a fifth that we will pull out as a constant. So now we have 1 over 5 and the power 5 summation of k to the power 4. And this is where now things have become a little bit interesting. What is k to the power 4 summed from k equals to 1 to k equals to n? So we do that in order to obtain this. I'm sure it's something that when you have enough practice, you could easily memorize these formulas. But this is how one would go about deriving it. So we know that k to the power 5 when summed looks like this. And so when you go ahead from, as you can see, 2 is equivalent to 1 plus 1. 3 is equals to 2 plus 1. And then n is the same as n minus 1 plus 1, right? And then we can add n plus 1 minus n. So this essentially would cancel out, but let's keep that there. So this now allows us to say that now we do have 1 plus 1 to the power 5, sorry, plus the summation from k equals to 1 to n of k plus 1 to the power 5. And because this goes up to this point, and now we are left with this subtraction here. Okay. So when we go ahead, what we do is when we expand k plus 1 to the power 5, first of all, in order to include this index here, we could now shift this to k equals to 0. So from k equals to 0 to n, and that now involves this one. So we don't have this lingering 1 to the power 5. So expanding k plus 1 to the power 5 means that we have now k to the power 5 plus 5k to the power 4 plus 1 to plus 10 k to the power 3 plus 10k squared plus 5k plus 1. And these binomial constants can be derived from Pascal's triangle. So for 1 is 1, for 2 items is 1, 1, for x plus y squared, you have 1, 2, 1. To the power 3, we have 1, 3, 3, 1. Just by adding these two successive. So 1 plus 2 is 3, 2 plus 1 is 3, and so on. And then for to the power 4, we have 1 plus 3 is 4, and then 3 plus 3 is 6, 3 plus 1 is 4, and then 1, 5, 10, 10, 5, 1. So using this Pascal's triangle, we are able to derive this constant here. So 1 for k to the power 5, 5 for k to the power 4, 10 for k to the power 3, 10 for k to the power 2, 5 for k, and 1 for okay. So now when we expand this, we now see that these two terms are the same. So we can cancel this out, and now we are left with 0 on the left-hand side. Now we have 5 times k summation of k to the power 4 plus 10 summation of k to the power 3 plus 10k summation of k squared plus 5 summation of k plus summation of 1 minus the n plus 1 to the power 5. Okay, so we can reorganize by shifting these terms onto the left-hand side, and then reorganizing it so that we have the unknown on the left-hand side. Now we can also push this term up to here onto the right-hand side, and now we are left the summation of k to the power 4 uh, can be obtained by dividing across that by 5. So we have now this n plus 1 to the power 5 divided by 5 minus we have this 10 divided by 5 is 2, so minus 2 summation of k to the power 3 from 0 to n, and then we have minus here, I apologize, minus and minus 2, since we have another 10 here, and then this 5 here divided by 5 is 1, and then since we have no constant here, we have a fifth. Okay, so we keep the minus here, the minus here, minus here. So we have now said, well, the summation of k to the power 3, we color code it as blue, summation of k squared, we color code it as green, summation of k, purple, and just this constant 1, we color coded it yellow. So then it's popular knowledge. We could also still derive it, but we don't want to spend a lot of time. The summation of k cubed from k equals to 0 to n is n squared times n plus 1 squared over 4. Summation of k squared is n plus 1 plus 2 n plus 1 over 6. And then summation of k from 0 to n is n times n plus 1 over 2. And summation of this constant 1 is obviously n. Substituting all that into now the equation for summation of k to the power 4 from k equals to 1, k equals 0 to n is going to be now n plus 1 over 5 minus 2. In place of summation of k to the power 3, we have n squared times n plus 1 squared over 4, and in place of k squared of n times n plus 1 times n 2n plus 1 over 6, and so on and so on. So this can be simplified further into a simple equation that is summation of k to the power 4 is 6n to the power 5 plus 15n to the power 4 plus 10n cubed minus n over 30. Therefore, our limit as n tends to infinity of the integral from x equals to 0 to x equals to 1 of the summation of from k equals to 1 to n of kx to the power 4 over n to the power 5 is equals to the limit as n tends to infinity of 1 over 5n to the power 5 times the summation of from k equals to 1 to n of k to the power 4. Now we know what this sum is. We just bring this entire expression in place of that summation. And so we put in bracket 6n to the power 5 plus 15n to the power 4 plus 10n to the power 3 minus n over 30. And then we can separate those individual items in the numerator so that we do have 6n to the power 5 over 30, which is n to the power 5 over 5. And then 15n to the power 4 over 30 is n to the power 4 over 2. And then 10n cubed over 30 is n cubed over 3. And then minus n over 30, which is minus n over 30. So as we go further, we see that this n to the power 5 and n to the power 5 cancel. So we have 1 over 5 times 5, which is 1 over 25, and then this divided by this, we have 1 over 10 to the power n, 1 over 10n, and then this is plus 1 over 15n squared minus 1 over 5 times that is 150, and then this n and this cancel, we have n to the power 4. So as n tends to infinity, we see that this entire expression goes to 0, this expression goes to 0, and this expression goes to 0. Because why? Because we have this n in the denominator, and as they tend to infinity, the entire fraction tends to 0. So we're left with now a 1 over 25 plus 0 minus 0. So our answer is 1 over 25. So the bigger challenge here was in finding what the summation of k to the power 4 from k equals to 1, or k equals to 0 to when k equals to n. So that expression just, I think, was a challenge. Maybe there are other ways to go around that. If you have any ideas about it, please share with us. We're here to learn, we're here to share, we're here to grow. So it was an absolute pleasure going through this problem with you. Until next time, adios. Thank you.
Problem number 2 of the quarterfinals, number 2, which is the definite integral from x equals to 0 to x equals to 1 of the natural log of 1 plus x squared plus x cubed plus x to the power 4 plus x to the power 5 plus x to the power 6 plus x to the power 7 plus x to the power 9 all over x. Very, very interesting problem. I hope you enjoy the solution.
It's a very interesting problem. And the first thing I personally like to do is to factorize whatever is under the log function. So 1 plus x squared plus x to the power 3 plus x to the power 4 plus x to the power 5 plus x to the power 6 plus x to the power 7 plus x to the power 9 can be factorized as follows. So I'd like to pair up some of these terms. 1 and x squared, these are the lowest terms, so I keep them like that. X to the power 3 and x to the power 5, I could pair those so that when I factor out x to the power 3, I get 1 plus x to the power 2, or 1 plus x squared. And then x to the power 4 and x to the power 6 could also be paired together, so that when we factorize x to the power 4, we still get 1 plus x squared, and x plus 7 and x to the power 9. And x to the power 9 could also be paired together, so that when you factor out x to the power 7, you still get 1 plus x squared. So then you go forward and then you do what we actually said. We pair these two, we pair these two, we pair these two. And then going forward, I pulled out x to the power 3 here, I pull out x to the power 4 here, I pull out x to the power 7. And then with these first two terms, I can factorize them by saying 1 plus x squared pulled out, we have 1 plus x cubed. That's the other factor that we can now multiply to that. And then here, when we pull out x to the power 4 plus x plus 4 and 1 plus x squared, we get 1 plus x to the power 3 left out, so we can keep that as another factor. So as you can see, we can factor this out, and then what we're left is 1 plus x squared times 1 plus x to the power 3 times 1 plus x to the power 4. This is what you get by factorization of this very long complex looking expression. So after that, now we can say that our integration now is simply the integration from x equals to 0 to x equals to 1 of the natural logarithm of the product of 1 plus x squared and 1 plus x cubed and 1 plus x to the power 4, all divided by x. And we can go forward and say, okay, let's use the rules of logarithm, where if you have a product of elements under the log function, that's the same as the independent summation of the log of these independent elements. So for example, for 1 plus x squared, 1 plus x cubed, 1 plus x the power 4, that all being under the log function can be expressed as log 1x plus x squared plus log 1 plus x cubed plus log 1 plus x to the power 4. And then obviously we can divide each by whatever was in the denominator, which is x. So our problem now has become a problem that involves solving three different integrals. Log 1 plus x squared over x, log 1 plus x cubed over x, log 1 plus x to the power 4 all over x. So just to make things interesting, I've color-coded these different integrals into blue, green, and purple respectively. Now let's focus on the first blue integral, which is the log integral from x equals to 0 to x equals to 1 of the log of 1 plus x squared all under x. Let's try to integrate that. So the first thing I'll do is I'll say let y be equal to log 1 plus x squared. And so e to the power y is equals to 1 plus x squared, and therefore e to the power y dy dx is equals to 2x, so that e to the power y over 2x dy dx is equals to 1, and therefore ey over 2x dy could be substituted for dx. Now we can express the x on the left hand side in terms of y. As you can see here, ey minus 1 square root would be the same as x. So ey over 2 times square root of e to the power y minus 1, all times dy could be substituted for dx. Now, as you can see, if we've substituted y for log 1 plus x squared when x equals to 0, we have log 1, and log 1 is 0. And then when x equals to 1, 1 plus 1 squared is 2. Therefore, y would be log 2. Therefore, the integration from x equals to 0 to x equals to 1 of the natural logarithm of 1 plus x squared over x is the same as the integral from y equals to 0 to y equals to a natural logarithm of 2 of y over square root of e to the power y minus 1 times e to the power y over 2, the square root times the square root of e to the power y minus 1. So this can be simplified further. And so we have pulling these two in the denominator out, we have a half times the integral from y equals to 0 to y equals to natural logarithm of 2 of y times e to the power y over e to the power y minus 1. Now, this part here can be expressed as the derivative of the natural logarithm of e to the power y minus 1, right? So that if we use our integration by parts, where if we have a integral of capital U dv, that's the same as the integral of capital U, it is the same as capital U times capital V minus the integral of capital V times the derivative of capital U, okay? So here our v is log e to the power y minus 1. So therefore uv is this y times that log e to the power y minus 1. Definitely applying the limits as required, minus the integral from y equals to 0 to natural logarithm of 2. And so v being log e to the power y minus 1, we keep it there. And then du, since u is 1, du is therefore just 1. And so this is what is left. Now, going forward, the upper limit as y tends to log 2 of y log e to the power y minus 1 at log 2. Therefore, these functions are continuous. and we see that we can separate this as the limit as y tends to log 2 of y times the limit as y tends to log 2 of log y minus 1, and that y tending to log 2, y equals log 2. At this point, we have log 2 here, but here, e to the power log 2 is the same as 2. 2 minus 1 is 1. Log of 1 is 0. So this upper limit would tend to 0. Same thing here. At the y equals to 0, we have this also tending to 0. And that is just self-explanatory. Okay, so we are left with the integral of negative, the integral of 0 from y equals to 0 to y equals to log 2 of the natural logarithm of e to the power y minus 1. And a half is kept out there. So now with this integral, we could say like let u be equal to log of e to the power y minus 1, and therefore e to the power u is e to the power y minus 1, and e to the power u du dy is equals to e to the power y, and therefore e to the power u over e to the power y. This is the same as, so e to the power y is the same as e to the power u plus 1 from here. And so e to the power u over e to the power u plus 1 du dy is equals to 1. And therefore you could substitute for dy with e to the power u over e to the power u plus 1 du. And so our integral here becomes half minus, as we know at 0, u tends to infinity since this becomes 1 minus negative infinity since it becomes 1 minus 1, and as this part tends to 0, the log of that would tend to negative infinity. And that's log to the power 2 would have 0. So we have, in place of log e to the power y minus 1, we have u. And then in place of dy, we put e to the power u over e to the power u plus 1, right? And then one thing we could do is with this sign, to remove this sign, we could just flip the limits. And then we could change, we could say let u be equal to negative u, and that would mean that where u is, we have a negative, such that this upper limit becomes positive. So the negative in this u and the negative with du cancel out, so we have a positive, and then wherever you see a u, you get a negative or a reverse sign. And so we have now a half times the integral from u equals to 0 to u equals to u tending to infinity of u times e to the power negative u over 1 plus e to the power negative u. And so this could also be expressed as negative minus 1 minus negative, like that. So that now we could express this as a geometrical series. So we have negative and we have this summation. Now we have put this negative here because we considered this e to the power negative u negative as the first term of the geometric series. And so when we put this negative here in this sum, we must put a negative here because this is positive. So we have a half times the integral from u equals to 0 to infinity of negative u summation of negative 1, since this negative here now, negative 1 to the power k times e to the power negative k to the power u, where e to the power u is the common ratio that when put into a geometric series and sum to infinity, you would get this expression. So we go forward, and then we put this u into the integral and take the integral into the summation sign. Um, and this is easy. This is trivial because if you have a series or if you have a sum of expressions and you try to integrate it, it's the same as integrating each specific term independently. And so that's what we've done. We've gone to integrate each independent item in the sum. And since we have this negative here, this expression is the same as u times the derivative 1 over k e the power negative k the power u. I mean, e the power negative ku. And so using integration by parts, this being v, and so it's being capital U, so uv is there for the product of these two, with the limits applied appropriately, minus, and keeping this as v, and then du being 1, since this is u, so derivative of this small u with respect to u is just going to be 1. And so continuing further, we do have negative 1 to the power k there, limit as u tends to infinity of u to the power u over k times e to the power negative ku, minus limit as u tends to 0 of u over k times e to the power negative ku. So the interesting thing here is if you express this in terms of 1 over k, u over k, u over k to the power, u over e to the power ku, using L'Hopital rule, since both will tend to infinity, both numerator and denominator, you could differentiate the numerator and the denominator respectively. And then the first derivative with the limit tending to infinity, as you can see, the u with respect to u when differentiated becomes 1, and this becomes negative k times e to the power k u. So the numerator tends to infinity, and the entire thing tends to 0. So this tends to 0. And with this is trivial since u tends to 0. This also tends to 0. And so we're left with the summation from k equals to 1 to infinity times a half of 1, negative 1 to the power k of negative 1 over k, the integral from u equals to 0 to infinity with the power ku. So that can be integrated easily. The integral of e to the power negative ku is the same as, since we have this negative, it becomes a positive 1 over k e to the power negative ku. And applying the limits appropriately, we're just left with k, since this tends to 0, and this would tend to 1 over k, right? And we still have a negative here, so that it becomes positive eventually. Now we have a negative here, okay? So the negative times this negative becomes a positive here, okay?
So on to problem 3 of quarterfinals number 2, which is the definite integral from x equals 0 to x equals to 1 of open brackets 1 plus the 2024th root of x close bracket all to the power 2024. What a good problem it looks.
So this problem, we have two methods that I would like to solve it with, and these two methods are kind of interconnected. But let's begin with the first method. So the first thing I would do is I would say, let u be equal to 2,024th root of x, such that u to the power 2,024 equals to x. And so 2,024 times u to the power 2,023 du dx equals to 1. And so 2024 u to the power 2023 du can be substituted for dx. Now, what is interesting is when x equals to 0, you would still be 0. When x equals to 1, you would still be 1. So when we do the substitution for 0, for x equals 0, we have u equals to 0. For x equals to 1, we have u equals to 1. And then for the 2024 root, we have u. And then obviously 1 minus u to the power 2024 times, in place of dx, we have 2024 times u to the power 2023. That's interesting because another way we would include this here is the same as 1 minus u to the power 2024 times the derivative of u to the power 2024. And so this can be expressed in the form of u dv, right? Where this is integration by parts, and u would be equated to 1 minus u to the power 2024, and v would be u to the power 2024, such that when you're doing integration by parts, it's the same as uv minus the integration of v du, right? So now, since we know our u and our dv, then our uv is therefore the product this and this. So we have u to the power 24 times 1 minus u to the power 24 with the limits given appropriately, minus now our du is the derivative of 1 minus u to the power 24, which is minus 2024 times 1 minus u to the power 2023 times our v, which is u to the power 2024. Now, with this, as we know, the limit of u tending to 1 for this, 1 minus 1 would be 0, so 0 times 1 would be 0, minus limit of u tending to 0, this u to the power 24 would tend to 0, so 0 times 1 to the power 24, this would be 0. And so we are left essentially with the integration of 2024 times 2004 times the integration from u equals to 0 to 1 with 1 minus u to the power 23 times u to the power 24. Now we can continue. Now u to the power 2024 can also be expressed as the derivative of u to the power 2025 over 2025. And then the process continues as follows. We have uv is the product of u to the 2025, the power 2025 over 2025 times 1 minus u to the power 2023. And so the constant now becomes 2024 over 2025. And as you can see, minus, keeping the same constant here, minus the derivative of 1 minus u to the power 2023 is the same as minus 2023 times 1 minus u to the power 2022. So continuing further, as we can see, the limit on the upper side of this limit, this here tends to 0 because 1 minus 1 to the power 3 is 0 times 1 to the power 5, so this is 0. And also when u tends to 0, 0 to the power 5 is 0 times 1 to the power 3 is also 0. So as we can see, this 2023 negative times this minus here, we get now 2024 times 2023 over 2025 times the integration from u equals to 0 to u equals to 1 of 1 minus u to the power 2 times u to the power 2025, right? And so the problem continues because now u to the power 2025 can also be expressed as the derivative of u to the power 2026 over 2026. Right? And then using again integration by parts, the process continues where in the denominator here, now we have 2025 times 2026. In the numerator, we have 2004 times 2023. And then this is V, this is U. Again, as you can see, the limit at 1 and limit at 0, this thing tends to 0. Minus, we again have the same constant, times 2022, which is the derivative of 2022 times 1 minus u to the power 2021, which is the derivative of 1 minus u to the power 2022. So this negative and this negative, we can interact and we have a positive. And so eventually we have now 2024 times 2023 times 2022 over 205 times 2026 times the integral from u equals to 0 to equals to 1 of 1 minus u to the power 2021 times times u to the power 2026. So this process really continues. And eventually, as we go on, we realize that 2024 times 2023 times 2022 times on and on up to maybe the value of k over 2025 times 2026, keeping on increasing up to 2024 plus 2024 minus k, and then times the integral from u equals 0 to 1 of u 1 minus u to the power k minus 1. As we keep going, times u to the power 2024 plus 2024 minus k. So this continues, it goes on and on and on until we arrive at the value of 1, right? And then in the denominator, we have 2025 times 706 all the way to 4047. And what we're left with the integral in the integral is u to the power 4047. And then that last integral now leads to now that constant multiplied by u to the power 2048, 4048 over 4048, and applying in those limits. This is 4048. We have 1 over 4048, right? And so this is the same as 2024 factorial because we have 2024 all the way multiplied up to 1. And then in the denominator, we have 2025 multiplied all the way to 4048. So we are missing in the denominator 2024 factorial to make it 4048 factorial. So we can put the 2024 factorial in the numerator, and now we have 4048 factorial in the denominator. So this is the same as 1 over 4048 factorial over 2024 factorial times 2024 factorial. So going forward, this means that we do have 2024 is the same as 4048 minus 2024. So this is 1 over the binomial constant or coefficient of 4048, 2024. And this is the answer for this interesting problem. There's also another way we could solve it. The second way would go about substituting for x with u, and so let u be equal to the 24th root of x, and so to the power 2024 would be equal to x, and so 2024 times u to the power 2023 du dx equals to 1. And so you can now substitute for dx with 2024 times u to the power 2023 du, right? And so going on, we just substitute as we said previously. But with these binomial expansion of 1 minus u to the power 2024, we have now the summation from k equals to 0 to 2024 of the binomial coefficient 2024 k. And then because we have a negative u, so we have times the power negative u to the power k times 2024 times 2023. U to the power 2023. So how we can go about we could now pull the constant out, 2024 out. Now we have the integral of the summation from k equals to 0 to 2024 of the binomial coefficient 2024 k times, now we pull the negative 1 out. We have times negative 1 the power k times u to the power k times u to the power 2023. So the u's can now be bunched together, and so we have negative 1 the power k times u to the power k plus 2023. And so since integration of a sum of elements the same as the sum of the integration of the specific element. So we can now push in this integration. Now everything else become a constant. Now we have to focus on the integration from u equals to 0 to equals to 1 of u to the power k plus 2023. So now focusing on the integral, we have now 1 over k plus 2024 times u to the power k plus 2024 with the limits applied appropriately. So we have our answer being 2024 times the summation from k equals to 0 to 2024 of the binomial coefficient 2024k times minus 1 to the power k times 1 over k plus 2024. And so our answer is the sum from k equals to 0 to 2024 from 2024 of the binomial coefficient 2024k times negative 1 to the power k times 2024 over k plus 2024. So what this tells us essentially is that the summation from k equals to 0 to 2024 of the binomial coefficient 2024k times negative 1 to the power k times 2024 over k plus 2024 is equals to 1 over the binomial coefficient 4048, 2024, right? Which is interesting because I could probably deduce that the summation from k equals to 0 to n of the binomial coefficient n k times negative 1 k times n over k plus n equals to 1 over 2n, something like that. This is a very interesting relationship that we learned from this integration, where n here is 2024, right? And 2n is 4048. And yeah, that's a nice relationship that we can deduce from this integral. So it's been an absolute pleasure going through this integration. It was cool. But yeah, if you have any question, if you have any doubts, any things you want clarify or suggestions for simpler methods, please feel free to leave your comment in the comment section. We'll be gladly would be waiting for that interaction. Thank you so much. Until next time, à la prochaine fois.
Another very interesting problem, which is problem number 1 of the MIT 2024 Integration Bee Quarterfinals number 3, which is the integral from x equals to 0 to x equals 2 pi of the cardinality of a set consisting of the floor function of sine x, floor function of cosine x, and floor function of tangent of x, floor function of cotangent of x. So at every value of x between 0 and 2 pi, you'd obtain the floor function of the corresponding values of sine, cosine, tangent, cotangent of x, and then obtain get the cardinality of that. It's an interesting problem. I hope you do enjoy following how we try and solve it.
This cardinality. Cardinality of a set is a measure of the number of elements of the set. For example, if we have a set consisting of elements x, y, and z, the cardinality of that set is 3 because we have 3 distinct elements there. If we have a set consisting of element x, 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 because we have the same element repeating 3 times, we would consider the cardinality of that set to be 1. And then if we had x, x, z, because we have 2 repeating elements, we would consider that 1, and then the extra one, which is the z element or the z element. And so the cardinality of this set would be 2. So that's what we're going to consider. Now, for our problem, we know what a floor function of a specific variable, for example, x, where it lies between two integers k and k plus 1, means that the floor function of that number or that variable would be k. That is the lower whole number integer. Um, yeah. So knowing that, and if we have the plots for sine x, cosine x, and tangent x and cotangent x, we see that there is variability, and we need to really split the 0 to the 2 pi. So 2 pi is here, and we have to split it into domains where we're able to distinguish um, the differences in terms of the number of elements, the specific elements within the set that we're given. For example, between 0 and pi over 4, which is here, we see that because sine x and cosine x are less than 1, they would all be 0, right? Because that's the lower integer. Right? And then tangent x, right? Tangent x would also be 0 because it's less than 1 at that point. Then beyond pi over 4, you see that it crosses tangent x crosses, so it's about here, it crosses 1 and begins to be greater than 1. So we see that tangent x becomes 1 for a small duration until it becomes 2, and then it continues from here onwards until it crosses the 3, becomes 2, like that. So I would have to divide these domains into small subdomains. So would have to have, for example, this domain would have to have from pi over 4 to pi over 2, and then from pi over 2 to 3 pi over 4, and so on. And then we begin to investigate these different functions independently. So let's say that we have 0 to pi over 4, pi over 4 to pi over 2, pi over 2 to 3 pi over 4, 3 to pi over 4 to pi, pi to 5 pi over 4, 5 pi over 4 to 6 pi over 4, 6 pi over 4 to 7 pi over 4, 7 pi over 4 to 2 pi. And for sine x, since sine x between 0 and pi over 4 is less than 1, that would be 0. Then from pi over 4 to pi over 2, again, is less than 1, would take that to be 0. The floor function of sine x would be 0. From pi over 2 to pi over 4, still under less than 1, and so the value of the floor function of that function is 0. From 3 pi over 4 to pi, since it's less than 1 at that point, it becomes 0. Now from pi downwards, we see that the value of sine x is less than 0, so the integer lower than 0 is going to be -1, and -1, -1, -1. Cosine x in the first interval would be 0, and then from pi over 4 to pi over 2, it's still less than 1, so it's 0, and then it crosses into the negative domain, and so now it begins to be -1, -1, -1, -1, and then it begins now to cross into the positive domain from 6 pi over 4, and then we have 0 and 0. Tangent x, since it's less than 1 between 0 and pi over 4, we have 0, and then it crosses +1 at pi over 4, so it becomes greater than 1. And then at pi over 2, we have it coming from a negative infinity, so it's less than -1. And we know that at pi, that's when now it at 3 pi over 4 is when it crosses -1. So in that domain up to pi, we have -1. And then it crosses 0 at pi. And so we have 0 greater than 1 at 5 pi over 4. And then from 6 pi over 4, we have it coming from negative infinity. And so it's less than -1. And then between 7 pi over 4 to 2 pi, it crosses -1 at 0. So in that entire regime, we have it to be -1. The same thing we do for cotangent x. And this is what we get. So what is the cardinality of this set at these different intervals? What does it tell us? It tells us that in this first interval, since all these are the same, the cardinality of the set there is 2. In the next domain, since again these and these are the same, so we have 2 distinct values, so that is 2. In the next one, since we have this and this being the same, so we have 1, 2, 3, so we have the cardinality of 3 in that regime. Here, since these are the same, we have 3 distinct. And here, since we have this being the same, we have 3 distinct elements. And here, since these are the same again, we have 3 distinct elements. And then here, since this and these are the same, we have 3 distinct elements. And here, since this and these are the same, we have 3 distinct elements. So essentially, our integral of the cardinality of floor function of sine x, floor function of sine x, floor function of tangent x, floor function of tangent x is the integral from 0 to pi over 4, where the cardinality here is 2. Here from pi over 4 to pi over 2 is 2. The rest of those regimes we have 3, 3, 3. And so we can now have 2 times pi over 4, since these are constants. 2 times pi over 4 plus 3 times pi over 4, 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 3 times pi over 4. So we have 1, 2, 3, 4, 5, 6, 6 threes. 6 times 3 is 18 plus 220 plus 222. So we have 22 times pi over 4, and that means we have 11 pi over 2 as our answer. So this is the answer for this interesting problem. I hope you did enjoy following along. If you have any question, it's a little bit tricky, but if you have any question, please don't hesitate to leave a comment in the comment section. Thank you so much. Until next time, à tout à l'heure, la prochaine fois.
On problem 2 of the quarterfinals number 3 of the MIT Integration Bee, which is the definite integral from x equals to 0 to x tending to infinity of 1 over in bracket x plus 1 times open bracket log squared x plus pi squared close bracket. Another very, very interesting problem.
The first thing that I would like to do is I substitute for the most complicated expression, that is log x. I'll say let u be equal to log x such that e to the power u equals to x. And so eu du dx, e to the power u du dx is equals to 1. And therefore, you could substitute for dx with e to the power u du. And so when also x equals to 0, what that means is that log x tends to negative infinity. And then when x tends to infinity, that means that log x also tends to positive infinity, such that the integral from x equals to 0 to x tending to infinity of 1 over x plus 1 times log x squared plus pi squared is equals to the integral of from u tending to negative infinity to u tending to positive infinity, or 1 over, in place of x, we're going to put this e to the power u plus 1, and in place of log x squared, we're going to put u squared plus pi squared. Now we can also go ahead and now pull this e to the power u here. Beg your pardon, I had forgotten to indicate that in place of dx, we can put eu du, e to the power u du. And so pulling this here so that now we have e to the power u over e to the power u plus 1 times u squared plus pi squared. The interesting thing here is that we can now split this integral as the integral from u tending to negative infinity to 0 to plus the integral from 0 to u tending to positive infinity. So we have two separate integrals. And it's the same integrand here, but we're just changing. We're trying to split it into the positive and the negative half of the interval or the integration interval. Now, what we can do here is, in order to change this into the positive domain, what we're going to do, we can just say let u be equal to negative u, such that wherever you see a u there, we have negative u. So you see e to the power u, we have e to the power negative u. E to the power u here becomes e to the power negative u. And since it's u squared here, this is even. So it's the same both in the positive and the negative interval. And then since du becomes negative du, so this negative here is shown here. And in order to cancel that negative, we can flip the interval. So we have the integral from u equals to 0 to u tending to positive infinity of e to the power negative u over e to the power negative u plus 1 plus times u squared plus pi squared. And then the next thing we can do for the second integral here, we can divide both the numerator for this second integral by e to the power u. And what that becomes is the numerator becomes 1, and the denominator here becomes 1 plus e to the power negative u times u squared plus pi squared. Now, combining those two integrals together, we have now in the numerator 1 plus e to the power negative u. And so as you can see, this and this cancel out, and we are left with the integral from u equals to 0 to u equals tending to positive infinity of 1 over u squared plus pi squared. And as you can see, this is the simplest integral now that we can handle. We'll just say let u be equals to pi tan theta. And so du d theta is equals to pi sec squared theta. And so we can substitute for du with pi sec squared theta d theta. And when u equals to 0, what that means is that pi tan theta equals to 0, and therefore theta equals to arctan of 0, which means that theta equals to 0. When u tends to positive infinity, pi tan theta tends to positive infinity, and tan theta tends to positive infinity, and therefore theta tends to pi over 2. So our integral now of u equals, from u equals to 0 to u tending to positive infinity of 1 over u squared over pi squared is the same as the integral from theta equals to 0 to theta equals to pi over 2 of 1 over pi squared in tan squared theta in place of u plus pi squared. And then here in place of du, we have pi sec squared theta. And so we can now do a couple of things. We can pull out pi squared here in the denominator and also pull out the pi in the numerator. And we have 1 over tan squared theta plus 1 sec squared theta. This part here is the same as sec squared theta. And so this 1 cancels with this squared here. And so we have 1 over pi times the integral from u theta equals to 0 to u theta equals to pi over 2 or 1 over sec squared theta times sec squared theta. So this and this cancel. So we are left with the integral of 1 from theta equals to 0 to theta equals to pi over 2. And so that's 1 over pi. And theta there is what is been obtained by integrating 1 with the interval 0 and pi over 2. So that's 1 over pi times pi over 2 minus 0. And that is 1 over pi times pi over 2. These pi's cancel, and so we are left with the half. And this is our answer. Very interesting. So that's how you solve this question. I don't think it was super complicated, but it was definitely very interesting. and it needed you to do some little acrobatics here and there to be able to get a more tractable problem. And so, thank you so much for following along. Until next time, à tout à l'heure, à la prochaine fois. Adios.
Problem number 3 of the quarterfinals 3, or quarterfinal number 3 of the MIT Integration Bee, which is the limit as n tends to infinity, or 1 over n times the integral from x equals to 0 to x equals to n of the maximum of 3 items, that is the fractional part of x, fractional part of root 2 times x, the fractional part of root 3 times x. Another very, very interesting problem. On to our problem. So the first thing that I feel inclined to do is doing some substitution. I would let u be equal to x over n, such that du dx is 1 over n, such that the product of n and du can be substituted for dx. And then looking at the limits, when x equals to 0, therefore u is 0. When x equals to n, u becomes 1. So this problem here becomes, for first of all, for the limits, we saw that it is 0 and 1 here, sorry. And then maximum of the fractional part, since n times u is x, where you see x, we have n u, and then square root of 2x becomes square root of 2 nu. Square root of 3x becomes square root of 3 nu, and then dx is n du. And we see that this n and this n would cancel out. Okay. So as we saw previously, we saw that obviously this n's cancel, and we have this beautiful integral of limit n tending to infinity of the integral from x equals to 0 to x equals to 1, the maximum of the fractional part of nu, the fractional part of square root of 2 times nu, and the fractional part of square root of 3 and nu. So since let's just try to understand what the fractional part bit means. So fractional part means is that excess of a real number beyond the integral part. So for example, if we have a fractional part of x, that's the same as x minus the floor function of x. So if we are to plot it, if you have the graph shown here, we have x-axis and then we have y-axis. The floor function, I mean, the value of x is obviously going to be that straight line, right? When x equals to 1, the value of x is 1, when x equals to 2. So it's just going to be a straight line. And then the floor function of x would be between 0 and 1, it's 1. Between 1 and 2, it is 1. Between 2 and 3 is 2. And between 3 and 4, it is 3. So the difference now is going to be between 0 and 1. It's going to be that value of x minus 0 for the entire part. So we just have x. But between 1 and 2, because the value keeps increasing beyond 2, the difference now is just going to be, again, the same value as what we would see in the domain 0 and 1. And it continues like that. So you have like a sawtooth wave like behavior, but the value is limited between 0 and 1. And that's the beauty of this function. It's called a sawtooth wave. Okay. Now, for this, since we know the behavior of the fractional part of x, but if you have the fractional part of nx, we decided to change u back to x. It means that at when x is equals to 1 over n is when you have that transition back. And then again, this is when we have x equals to 2 over n, right? And then for the fractional part of uh, square root of 2 nx, the transition is at 1 over square root of 2n, 2 over square root of 2n. And then for square root of 3 nx, the same thing, we have 1 over square root of 3n is when you see that transition. So the maximum of this part of this function, all these values lie between 0 and 1, but we're asked to extract only the maximum at any given interval of the three. And we see in that region, in this domain, this is the maximum. In this domain, we have this as the maximum. In this domain, we have this as the maximum. In this domain, we have this as the maximum. This as a maximum here. This is the maximum for a short interval between this comes in. But as you go on, it becomes stochastic. You know, there's just random values being the maximum, but all lying between 0 and 1. So what this tells us that this integral here is the same as the integral from 0 to 1 of the value of x being obviously 0 and 1 within that, but times a certain probability. So we have to find the probability for which this the value of x shows up, right? As we integrate between 0 and 1. That is what it's telling us. It's more of an expected value of x, given x is the maximum of the three different independent variables, and we need to figure out what is that probability. What's the probability for which that a given value of x shows up, right? Now, we do have what we call, since these independent variables have a uniform distribution, if you have a value like this, right? If you have what we call the cumulative distribution function, if the distribution is uniform, then the CDF or cumulative distribution function fx is going to, at the value of x, is going to be x minus the lowest value 0 over the total, which is 1. It's going to be 1 here minus 0. And in this regard, we have x as the CDF for any of those variable fractional part of nu, fractional part of square root of 2 nu and x, and so on. So taking everything into consideration, for the maximum value, it means that we have three different variables that are independent, but also less or equal to 1. And this same as the product of the CDF of each event, right? Which is x times x times x, which is x cubed. But we know that the probability at any given value of x is the derivative of the CDF. So which is the derivative of x cubed, which is 3x squared. Now our integral now becomes the integral of x from x equals to 0 to x equals to 1 of x times fx. We know fx to be 3x squared, and so we have it become the integral from of 3x cubed, and which is, we have 3 out here, and x cubed integrated is x to the power 4 over 4, so with limit 0 and 1. And so that means that the answer is 3 over 4. So this is a very tricky problem, but it just did require a little bit of acrobatics here and there. Now, until next time, it's been an absolute pleasure hanging out with you. For those of us who haven't subscribed, we do really encourage you to subscribe to our channel. But otherwise, see you next time. Problem number 1 of the quarterfinals number 4, MIT 2024 Integration B, is the indefinite integral of e to the power 2x over, open bracket, 1 minus e to the power x, close bracket, to the power 2024.
So this problem is interesting. For me, what I usually do is I look at the most complicated expression, and then I try and substitute for that. So I'll say let u be equal to 1 minus e to the power x, such that du dx is equals to negative e to the power x, such that du is equals to e to the power x dx. And so what is minus e to the power x in terms of u? It's the same as 1 minus u negative. And so we divide both sides by negative 1 minus u. And so negative du over 1 minus u can be substituted for dx. And so pulling out our problem, and we say, okay, the integral of e to the power 2x over 1 minus e to the power x to the power 2024 is the same as 1 minus e to the power u, which is e to the power x. Then we square that to make it the power to make it e to the power 2x. And then in the denominator, we say let u be equal to 1 minus the power x. So we say now the denominator is u to the power 2024. Now, in place of dx, we say negative du over 1 minus u would be substituted for that. And so 1 minus u here in the denominator, 1 minus that cancels with the 1 square here. So we are left with a negative 1 minus u over u to the power 2024. Now that's our integration. We can now use the sign, multiply the sign across. So we have u minus 1 over u to the power 2024, and we divide u to the power 2024 across, so we have 1 over u to the power 2023 minus 1 over 2000 u to the power 2024. So these are easily integratable polynomials. So we now have the integration of 1 minus u to the power 2023 is the same as negative 1 over 2022 u to the power 2022. And then the integration of negative 1 over u to the power 2024 is the same as plus 1 over 2023 u to the power 2023 plus the integration constant. Now, since we say that let u be equal to 1 minus e to the power x, we're just going to plug 1 minus e to the power 2x in place of u where u appears. So the integral of e to the power 2x over 1 minus e to the power x to the power 2024 is negative 1 over 2022 times 1 minus e to the power x to the power 2022 plus 1 over 2023 times 1 minus e to the power x to the power 2023 plus the integration constant. Now we can, bring the positive out first and then follow with the negative component, and then followed by the integration constant. So what was provided in the answers is 1 over 2023 times 1 minus x to the power 2023 minus 1 over 2022 times 1 minus e to the power x to the power 2022 plus the integration constant. And so this is the answer for this seemingly integrate problem. It is actually easy to solve it. Thank you so much for those of us who followed through. If you have any question, please don't hesitate to leave a comment on the comment section. If you do have a variation on how this problem could be solved, please, we would love to hear from you and would love to share your version of the solution with the rest of our audience. Thank you so much for the support. Thank you again for following us. Until next time, à tout à l'heure, à la prochaine fois, et adios.
Problem number 2 of the MIT 2024 Integration Bee Quarterfinals number 4, which is the limit as n tends to infinity of log to the base n, open brackets, the integral from x goes to 0 to 1, open bracket, 1 minus x to the power 3, close bracket to the power n. What an interesting problem. I hope you do enjoy looking and following along in the solution.
So this problem is interesting, and I would like to, as usual, I would like to substitute for the most complex term in this integral. That is x to the power 3. So what I do is I say let u be equal to x to the power 3 because I just want to create that abstraction that takes my mind away from the complexity in that expression. So what happens there is that du dx is the same as 3x squared, and thus du dx is 3u to the power 2 over 3, because now we've expressed x squared in form of u. Because if you look at this, the cube root of u would be equal to x, and therefore x squared would be u to the power 1 over 3 times the power 2, which is u to the power 2 over 3. And so that's what we've obtained here. Now, dividing both sides by 3u to the power 2 over 3 results in du over 3 to the power 3u to the power 3 being something that would replace dx with. Now, as you can see, when x equals to 0, x to the power 3, or 0 to the power 3 is 0, so u is also 0. When x is equals to 1, 1 cubed is the same as 1, and so u would also be 1. So the limits don't really change, and so our problem now becomes a limit as n tending to infinity of the log the power to the base n, of the integral from x equals 0 to 1 of 1 to minus x to the power 3 to the power n is the same as limit as n tends to infinity of log the power n. The integral now becomes integral from u equals to 0 to u equals to 1, or 1 minus, in place of x to the power 3, we have u, so we have 1 minus u, close bracket, the power n. And in place of dx, we have du over 3 to the power u. 3 times u to the power 2 over 3. And we can decide to maybe pull out the 3 out. So we have 1 over 3 outside the integral sign. And then u can now be expressed, u to the power 2 over 3 can be expressed as u to the power negative 2 over 3. So this is good. We have that problem. Now, one other thing we could probably do is just express u first, then 1 minus u to the power n would follow. So we have a problem here that we can solve in 2 major ways. I'll begin by the simple way, the way that we are taught when we begin calculus, and we'll use the solution that involves integration by parts. Okay, so if that is our integral, we go forward and say, okay, we do have this 3 and u to the power negative 2 over 3. That's the same as the derivative of u to the power 1 over 3. So if you have an integral of capital U, d capital V, The solution, as we are taught when you tackle integration by parts, is the product of capital U and capital V minus the integral of capital V d, the derivative of capital U. Okay, so in this situation, we have our V as u to the power 1 over 3, or the cube root of U. And then our capital U is 1 minus u to the power n. So our uv would be the product of u to the power 1 over 3 and 1 minus u to the power n, and applying the limits appropriately, plus now the derivative of u is now n goes down, derivative of u is negative 1, so the minus here and the negative that comes from differentiating 1 minus to the power n now would interact and we have a plus here. So we have the integral now of from 0 to 1 of 1 minus u to the power n minus 1 now, because we differentiated this 1 minus u to the power n. And then we've now kept v, and so v is u to the power 1 over 3. So limit as u tends to 1 on the upper limit, 1 minus 1 would be 0, so 0 times 1 here, that this entire thing becomes 0. And then limit as u tends to 0, when u equals to 0, so this becomes 0, so the entire thing goes to 0. This collapses to 0, right? And so the effective integral, this integral here is the same as n times the integral from u equals to 0 to equals to 1, or 1 minus u to the power n minus 1 times u to the power 1 over 3. We go to the same thing now. U to the power 1 over 3 is the same as 1 over 1 plus 1 over 3 times the derivative of u to the power 1 plus 1 over 3, right? And so we can now pull this constant out. So we have n over 1 plus 1 over 3 times the integral from u equals to 0 to 1 of 1 minus u to the power n minus 1 times the derivative of 1 plus 1 over 3. So again, we repeat the process here. We consider this as something that we could use integration by parts. So this becomes v, and this is u, and the process continues again. So now we have this constant out, and then so uv is 1 minus n 1 minus u to the power n minus 1 times u to the power 1 plus 1 over 3. And so continuing forward, the derivative of 1 minus u to the power n minus 1 is now n minus 1 times 1 minus u to the power n minus 2. So we've multiplied the n, now n minus 1, and the denominator remains the same. And so here again, as you can see, at the upper limit, when u equals to 1, this becomes 0. When u equals to 0, this becomes 0. So this entire thing again goes to 0. Now we continue down. Now the process continues. It continues. And again, we use integration by parts, right? And u to the power 1 plus 1 over 3 is the same as 1 over 2 plus 1 over 3, the derivative of u to the power 2 plus 1 over 3, right? And so the process continues on and on until we exhaust all the n's, right? So we have the process going on all the way until from n to 1, right? And then from 1 plus 1 over 3, 2 plus 1 over 3, all the way up to n plus 1 over 3. So this is our solution, because when now this n minus 2 degenerates to 0, this becomes 1, and we could easily now just integrate this u plus n minus 1 over n minus 1 plus 1 over 3. And so that becomes an easy thing. So this is our answer for just the integral part. We haven't really tackled the limit. So how we could tackle this semi-integral in a different way is we could use the beta function. I've seen a lot of comments in our comment section, people encouraging us to use beta functions. This is something that probably would be common to anyone who has done a applied mathematics, and that is the beta function of z1 and z2 is the integral from t equals to 0 to t equals to 1 or to the power z minus 1 z1 minus 1 bracket 1 minus t z2 minus 1. So we can express this in form of this, only that obviously here we have u and here we have t. So I can express negative 2 over 3 as 1 over 3 minus 1. And then 1 minus u to the power n can be expressed 1 minus u to the power n plus 1 minus 1. So z1 here is a third and z2 here is n plus 1. So this becomes now limit as n tends to infinity of log to the base n of 1 over 3, beta function of a third, and n plus 1. So beta function can be expressed as a combination of gamma functions, which is now the, keeping this a third here, gamma of function of 1 over 3, gamma function of n plus 1 over gamma function of 1 over 3 plus n plus 1. Right? So going forward, we can now express the gamma function of n plus 1 as n times the gamma function of n, and also the gamma function of third plus n plus 1 is the same as 1 over 3 plus n times the gamma function of 1 over 3 plus n, right? And this can go on and on and on and on until now this becomes 1. So in other words, gamma function of n plus 1 is the same as n factorial. And then for the denominator also, it becomes now 1 over 3 plus n all the way up to 1, or all the way up to the gamma function of a third, right? And now this gamma function of a third can cancel with the gamma function of a third here. And now we are left with a third times the n factorial over 1 over 3 times plus n, 1 over 3 times 1 over 3 times n minus 1, all the way up to 1 over 3 plus 1. Okay, so we've tackled the integral part, and it's obvious here that this constant here can, using the law of a logarithm, we can have two separate logs, because there's multiplication here, so we can just add this, and with the limit n tending to infinity, this just becomes 0. So our focus now just becomes the limit of n tending to infinity of this second term here. In other words, n factorial over in 1 over 3 plus n times 1 over 3 plus n minus 2 all the way to 1 over 3 plus 1. So we can then use Starling's approximation, which tells us that if you have n factorial, this is can be approximated as n becomes larger with the square root of 2 pi n times n over e to the power n. And we can show that with the plot here. So we are plotting x factorial. On the x-axis, we have x. On the y-axis, we have x factorial. And as you can see, white is the plot of x factorial. And then blue is the plot of the Starling approximation. As you can see, they really approximate each other very well. So we can use Starling's approximation to now replace the factorial terms. So in other words, our problem now approximates to limit of n tending to infinity of the log the base n of 2 pi square root of 2 pi n times n over e to the power n in place of n factorial, and in place of the n 1 over 3 plus n quasi-factorial, we could use the same. So square root of 2 pi in bracket n plus 1 over 3 times n plus 1 over 3 over e to the power n plus 1 over 3. And so using the rules of logarithm, we can now separate the 2 pi's first of all can cancel out because these are constants. This can go away. But now we can use the rules of logarithm to separate the numerator and the denominator. So for example, here, square root of n is the same as log to the base n of n, half on the other side, minus, since it's also square root, a half of log the base n of n plus 1 over 3, plus, going back here, since this is a power, so this becomes a constant. So n times log the base n of n over e minus getting back the denominator. This power here becomes now something on the left-hand side of the natural log of the log to the base n. So n plus 1 plus 1 over 3 log the base n of this n plus 1 over 3 over e, right? So if we express this problem this way, I think it's easy to really handle things. This is easy because it's the same as n, same base, so this becomes 1, right? And here we could also, because a third is just a small increment over n, and when n tends to infinity, so this also becomes 1, right? And then now we can combine these two. So we can go ahead and say, because we have this and this, so we have n log n over n plus 1 over 3. And as you can see, if we divide across by n, so we have n here, so that as when n becomes too large, this really tends to 1, and so the log to the base n of 1 will be 0, so this becomes 0, and we said this tends to 1, and this tends to 1, right? And here, this is interesting because, again, we could separate it out so that we have log n of n, log to the base n of n plus 1 over 3 minus log to the base n of e, so that since this is a small constant relative to n, when n tends to infinity, that part goes to 0, and this part goes n base, same base, and also same number. So this would tend to 1, right? And so we have now a half, because a half times 1 minus a half, and plus 0 minus a third. So this and this would cancel. So we are left with negative 1 over 3 as our final answer. So this is interesting. This has been a very interesting problem. I hope you really enjoyed following along. Definitely knowledge of Starling's approximation kind of seemed like the important principle that would enable one to connect it to the answer. So if you have any questions, if you have alternative methods on how to go about solving this problem, please, we welcome them. We do welcome those suggestions. Thank you. Until next time, at the local question forum. Yes.
To the last problem of the quarterfinals series of MIT 24 Integration B, which is problem number 3, quarterfinals number 4, MIT 24 Integration B, which is the indefinite integral of sine x over 1 plus sine x times cosine x over 1 plus cosine x. Interesting problem. I hope you do enjoy following along as we try to solve it.
First thing with this problem, I personally, what I would do is I like to express it in a way that could be integrated using the natural log approach. So if we look at the denominator, 1 plus sine x times 1 plus cosine x, that's the same as 1 plus sine x plus cosine x plus sine x cosine x. Therefore, the numerator sine x cosine x is the same as 1 plus sine x times 1 plus cosine x minus sine x minus cosine x minus 1. And using the identity sine squared x plus cosine squared x equals to 1, we can replace the 1 here with the sine x, cosine x, sine squared x plus cosine x. And therefore, if we do go ahead and plug whatever we have here in the numerator here, that will help us quite a bit. So let's go ahead and then plug that in the numerator. So the integral of sine x over 1 plus sine x times cosine x over 1 plus sine x, the same as the integral of 1 plus sine x times cosine 1 plus cosine x minus sine x minus cosine x minus sine squared x minus cosine squared x, right? Over 1 plus sine x times 1 plus cosine x. So the first component here, obviously, we will cancel with the denominator. So essentially, this and I mean, let's try to separate things around. So that will cancel. So we have a 1 there minus sine x plus cosine x plus sine squared x plus cosine x over 1 plus sine x times 1 plus cosine x. Now we can collect like terms together, sine x and sine squared x. Those could be pulled together such that we can then go ahead and factorize. And then one of the item in the denominator can go away, and then same thing goes ahead. That will happen in the second part where we factorize the cosine squared x terms, right? So we've grouped sine x and sine squared x where we pull out sine x. So we have this and that canceling. And then for the cosine x times, that and that cancels out, right? So we are left with now 1 minus sine x over 1 plus cosine x minus cosine x over 1 plus sine x. This can easily be integrated. So for 1, that's the same as x plus sine x over 1 plus cosine x can be integrated to natural logarithm of 1 plus cosine x minus cosine x over 1 plus sine x is the same as natural logarithm of 1 plus sine x, and then plus the integration constant c. So this is the simpler approach that one could use. And it did require somebody to have that intuitive way of figuring out what the numerator required. But if you don't have that intuitive approach, the next method would be a good one. First of all, obviously, we can group these two log terms into one single log function, which is x plus natural logarithm of 1 plus cosine x over 1 plus sine x plus the integration constant c, right? So then there's a method too that probably would appeal to the less intuitive approach to it, and that is we could use the half angle approach. So sine x over 1 plus sine x times cosine x over 1 plus cosine x could be now expressed in the half angle formalism where sine x is the same as 2 sine x over 2 times cosine x over 2 times cosine x is the same as cosine squared x over 2 minus sine squared x over 2. And then obviously 1 plus sine x is 1 plus 2 sine x cosine sine x over 2 cosine x over 2. And then cosine 1 plus cosine x is the same as 1 plus cos squared x over 2 minus sine squared x over 2. Then we can say let u be equal to tan, let u be equal to tan x over 2, right? Such that du dx is the same as half sec squared x over 2. And therefore, what that means is that we have 2, this multiplying both sides by 2, 2 du over sec squared x over 2 is equals to dx when we multiply dx on both sides. And that means that now 2 du over tan squared x over 2 plus 1, since sec squared x over 2 is the same as tan squared x over 2 plus 1, means that now expressing this tan squared x in terms of u, the same as 2 du over u squared, the tan squared x same as u squared, plus 1. And so we can substitute dx with 2 du over u squared plus 1. And if you have a triangle and the base angle is x over 2, it means the hypotenuse, the opposite is u, and then the base is 1. Since a tangent of that base angle is the same as opposite over adjacent, and therefore the hypotenuse becomes square root of 1 plus u squared, obviously using the Pythagorean theorem. And therefore, since we know that our equation is this, then for where sine x over 2 is the same as opposite over hypotenuse, which is u over square root of 1 plus u squared. Cosine x the same as base over hypotenuse, which is 1 over square root of 1 plus u squared. The same thing here, cosine squared is 1 over 1 plus u squared, since we have this 1 over square root of 1 plus u squared squared. And then sine squared x the same as u over 1 square root of 1 plus u squared. All that squared, so we get u squared over 1 plus u squared. And so we do apply the same thing for 2 sine x over 2 and cosine x over 2. And then for cos squared x, the same term here, since it's here, we can take this same thing down here. And then for dx, we have 2 du over u squared plus 1. Okay, as we continue simplifying that, it means that when we multiply this to the square root of 1 plus u squared, it becomes 2u over 1 plus u squared. And then here, since the base is the same, so we have 1 plus u squared in the denominator, and then 1 minus u squared in the numerator. And then here again, obviously the same thing happens. So we have 2u over 1 plus u squared, and then plus 1 here, and then there's plus 1 minus, again here, 1 minus u squared over 1 plus u squared. So simplifying things further, pulling these 2 out, and then multiplying the denominator with this constant term here, 1. So we have 1 plus u squared plus 2u over 1 plus u squared, and the same thing here, 1 plus u squared plus 1 minus u squared over 1 plus u squared, right? So going on, this 1 plus u squared plus 2 is the same as 1 plus u squared. And then here, this term and this term goes away, so we have only 2. So the thing that we can see here is that this and this goes, this cancels with this cancels with this. Now we're left with u times 1 minus u squared over 1 plus u squared times 1 plus u squared. This 1 plus u squared comes here, right? Then we can now factorize 1 minus u squared, the same as 1 minus u times 1 plus u, so that one of the 1 plus u in the denominator cancels with that. And so the integration becomes 2 times the integral of u times 1 minus u over 1 plus u times 1 plus u squared. So we can now use, we can try now to simplify this fraction. Can decompose it a little bit, but first of all, we'd have to multiply u across, right? So the first thing I would do is I would say 1 minus u squared over 1 plus u times 1 plus u squared is equivalent to a constant over 1 plus u plus bu plus d over 1 plus u squared. Then I can multiply this denominator across so that u minus u squared is equals to a times 1 plus u squared plus b u plus d times 1 plus u. So multiplying things out, we find that a plus d plus b plus d times u plus a plus b um, times u squared. Since we don't have any constant here, then it means that a plus d is 0. And since we have a constant of 1 here, it means b plus d equals to 1. And then a plus b is equals to negative 1, since the constant behind the u squared is negative 1. What this means is that since we have a plus d equals to 0, it means that a equals to negative d. And then since a is the same as negative d, we substitute negative a in place of d here. It means that b minus a is equals to 1. And therefore, so using this, negative a plus b equals to 1. And we know that a plus b equals to negative 1. And we add these two equations. We have a simultaneous equation here. This plus this means that the a cancels out, and we have 2b equals to 0, since 1 plus negative 1 is 0. That means that b is 0. And so we can go back and say, okay, since we know that b minus a equals to 1 and b equals to 0, it means negative a equals to 1, and therefore a is equals to negative 1. And therefore, since a equals to negative d, then it means that d is 1. Okay, so we know that a is negative 1, b is 0, and d is positive 1. So if our integral 2 times the integral of u minus u squared over 1 plus u times 1 minus u squared is equals to 2 times the integral of a plus a over 1 minus a plus u plus b of u plus d over 1 plus u squared. This means that's the same as the integral of 2 times the integral of negative 1 over 1 plus u plus, since b is 0, we have 1 over u squared. This can easily be integrated, since this is just the same as negative 2 natural logarithm of 1 plus u. And then this, the integral of 1 plus 1 over 1 plus u squared is the same as arctangent of u. So we have 2 times arctangent of u, and then obviously plus the integration constant. But since we know that u is the same as the tangent of x over 2, that's what we substituted u with, or we substituted x with. And then it means that where we have u here, we have tangent x over 2, and then we have u here is the same as a tangent x over 2. So here, obviously, things are easy. That means that the arctangent of tangent of x over 2 is the same as x over 2. So we just have 2 here times in bracket x over 2. This 2 would cancel, so we have x. And then the next focus would just be now to focus on simplifying whatever is under the log sign. And so the log function. So we have tangent of x over 2 is the same as sine of x over 2 over cosine x over 2. And so what that means is that when we can simplify this further by saying this is the same as cosine of x over 2 plus sine x over 2 over cosine x over 2. And then these two can go up here using the rules of logarithms. That means that now we have a negative natural logarithm of cosine x over 2 plus sine x over 2 over cosine x over 2 squared plus x plus c, obviously c being the integration constant. And so when we square the numerator, we get cosine squared x over 2 plus sine squared x over 2 plus 2 sine x over, so the next cosine x over cosine squared x. So cosine squared x over 2 plus sine squared x over 2 is the same as 1, so we have 1 plus, and then 2 sine x over 2 plus cosine x over 2 is the same as sine x. Then we still have cosine squared x over 2 in the denominator. So cosine squared x over 2 is the same as a half cosine squared x over 2 plus a half cosine squared x over 2, right? And obviously we have x in integration constant c. That means that now we have now log, negative natural logarithm of 1 plus sine x over half cosine squared x over 2 plus a half cosine squared x over 2 is the same as 1 minus sine squared x over 2. Since we have the identity sine x squared over 2 plus cosine squared x over 2 equals to 1, so cosine squared x over 2 is the same as 1 sine squared x over 2. So substituting that in place of cosine squared x over 2, that means that now we have half cosine squared x over 2
minus half sine squared x over 2 plus a half. Now we can pull that constant half out. What that means that now we do have 1 over sine x over half cosine squared x over 2 minus sine x squared x over 2 plus 1. Now this cosine squared x over 2 minus sine squared x over 2 is the same as cosine x. So we can now write that this is the same as negative natural logarithm of 1 plus sine x over half cosine x plus 1. So using the laws of logarithm or rules of logarithm, we can pull this half out since the product of these two numbers is the same as the sum of the logs of the independent terms. But since it's in the denominator, we can now just put a negative. So we have minus natural logarithm of 1 plus sine x over cosine x plus 1 minus log half plus c plus x plus c. So this is a constant, and we can bunch it with this constant so that eventually now we do have minus log 1 plus sine x over cosine x plus 1 plus x plus c, because this is just a constant that can be bunched together with that constant. And so we can, by reversing now these items so that the negative sign goes away. So we have x plus natural logarithm of 1 plus cosine x over 1 plus sine x plus c as our answer. So this is obviously a much winded or solution to the problem, but it is all the same interesting, just showing you that however way you try to solve it, I think the answer should be the same. But yeah, it was an absolute pleasure solving this problem, and I hope you do enjoy following along. Until next time, bye bye, and yeah, I was please, if you haven't subscribed, please subscribe to our channel. Just help us give us that extra visibility. Thank you. Till